Let's talk about comparison theorems. Now, if your function is greater than 0 on this closed interval from a to b, then when we look at the area under the curve, that is the definite integral from a to b of f of x dx, this will also be greater than or equal to 0. So just as a quick reminder, this is the area, right? This is the area. Okay, under f from A to B. Okay, so if you look at the second comparison theorem, instead of comparing f of x to the number 0, we're comparing f of x to some other function, g of x. So let's say that f is greater than or equal to g on this closed interval from A to B. Then what we could do is we can compare the integrals of the two. So we got the integral from A to B of f of x dx, and we got the integral from A to B of g of x dx. And if f of x is bigger than g of x, then its integral, that is the area under the curve, will also be bigger or equal to. Okay? This last one, for part C, I created a little picture on the left-hand side to help you understand this picture a little bit better. So let's say that your function f is bounded between two numbers, lowercase m and capital M. So in this picture, my function f is going to be given by the blue curve, that's f of x. And my lowercase m is going to be given by this red line, small m. And the uppercase m is represented by the green line up top, that's capital M. Okay. So then what do we have? Well, I hope that we can all see that the area underneath the lowercase m function, so this area right here, this red area, this area is going to be less than the area under the curve. So that red area I just shaded is the area of a box. So that's m, that's the height of the box, times the width of the box is b minus a. Okay, and what I'm saying is that the blue area underneath this curve is going to be bigger than this red area. So that's captured by this inequality right here, this inequality right here. All right, if I look at the area under the capital M, that is, if I look at the area under this gigantic rectangle here that I'm currently shading in green, this area in green is going to be bigger than the area under the curve, right? In other words, that green area is going to form an upper bound. So the green area is going to be given by capital M times B minus A. And again, both of these things are just the area under a box. It's the area of a rectangle, which is, of course, the height times the width. Okay, so we're essentially saying we can bound the area of f between the area of the red box and the area of the green box. Why don't we take a look at a quick example? In example 7, we want to compare two functions. We have f of x is equal to the square root of 1 plus x, and g of x, which is the square root of 1 plus x squared. And it's really important that we're looking at over the interval from 0 to 1. Okay, so I want to highlight that. I want to emphasize that the fact that we're over the interval from 0 to 1. Now, here's the question. Which function is bigger on the interval from 0 to 1? And if you look at these guys, these two functions, f of x and g of x, they kind of have the same shape, right? It's square root of 1 plus, and we're really left with ending up comparing which is bigger, x or x squared, right? So this question actually becomes which is bigger on 0, 1, x or x squared. So originally we were trying to compare which was bigger, f of x or g of x. But due to the shape of the functions, I'm really left with comparing which is bigger, x or x squared. So if we just draw a quick little set of axes over here, we're going to get, there's the y-axis, here's the x-axis, here's 0, here's 1. What we see here, and here's another 1, so this point here is 1, 1. And this origin point is 0, 0. What we see that we're doing here is we're really comparing the graph of x, which is just a straight line, and we're comparing that with the graph of x squared. So this was x. We're comparing that with x squared, which is a parabola. So this guy kind of comes up like this. This is x squared. All right. And what we can see is that when we're restricted to the interval from 0 to 1, x is actually bigger than x squared, right? So x is greater than x squared on this interval from 0 to 1. So this implies that f of x equal to the square root of 1 plus x is actually going to be greater than g of x, which is equal to the square root of 1 plus x squared. All right, so I'm going to highlight this because this basically is our final answer. We're just looking to compare these two. When you take second semester calculus, we use this idea of comparing one thing to another quite a bit. So this is sort of a preview of all of that. All right, everyone, take care.